Hello class, this is section 2.3, more graphs for quantitative data. I am your instructor William Buellman and this is Stat 1200. So our objectives for this section are to be able to construct stem and leaf plots, construct dot plots, and to be able to construct time series plots. So as always, we're going to start off with a definition. Stem and leaf plots are a simple way to display small data sets. In stem and leaf plots, the rightmost digit is the leaf and the remaining digits form the stem. We construct a stem and leaf plot by using the following three-step process. So first we make a vertical list of all the stems in increasing order and draw a vertical line to the right of that list. We go through the dataset and for each value we write its leaf next to its stem. For each stem we arrange them in increasing order. So here's an example. So I see that I have 1, 2, 3, 4, 5. And I'm going to draw the vertical lines because I have the 10s, the 20s, the 30s, the 40s, and the 50s. So now each stem that I see, I'm just going to write it. So first I see 11, so there's a 1, then 12, there's a 2, then 15, there's a 5, then another 15, there's a 5, then a 16, that's a 6, and then a 12, that's a 2. So those are all the ones that start with 1. So now I'm going to do the 20s. 0, 7, 9, 7, 2, 1, 0. Next the 30s, so I have 39 and 31. Now the 40s, I have 45, 46, and 45. And now the 50s. 7, 2, 8, 0, 5. So this isn't a finished stem and leaf plot. This is our first step. So now we want to reorganize the leaves in order from smallest to largest. So again, I write the stems, but now I'm going to go, okay, we have a 1, then a 2, then another 2, then a 5, 5, and 6. So now I've reorganized the stems for the tens place. So now I'm going to do the same thing for the 20s. So we have 0, 0, 1, 2, 7, 7, 9. So now, again, we continue on. 30s, 1, 9. The 40s, 5, 5, 6. And the 50s, 0, 2, 5, 7, 8. So now this is our finished stem and leaf plot. We have our stems here on the left-hand side, our leaves on the right-hand side, and our leaves are organized from smallest to largest. So the first stem and leaf plot we have on the left-hand side is a working step to get us to our finished stem and leaf plot on the right-hand side. So here we have another definition for what we call a split stem. Sometimes one or two stems contain most of the leaves. When this happens, we often use 2 or more lines for each stem. This plot is then called a split stem and leaf plot. So each stem in a split stem and leaf plot must receive the same number of lines. So if we split the 10s into 2 lines, then the 20s have to be split into 2 lines, and the 30s. So we have to be consistent. Here are the steps we're going to do. We're going to make a vertical list of all the stems in increasing order and draw a vertical line to the right of the list, same as we did before. Go through the data set and for each value, write the leaf next to the stem. Again, same thing as we did before. For each stem, arrange its leaves in increasing order. Again, same as we did before. So it's a very similar process, it's just slightly different. Alright, so here's example 2. So in this case, we have decimal values, right? We have 1.5, 0.9, 1.1, etc. So our stems here are going to be what's to the left of the decimal. So 1, 0, 3, those. So we have 0, 1, 2, 3, 4, 5, and 6. If we look at all of our numbers, those are the stems we're going to need. So now the leaves, I'm going to already do them in increasing order. You can do that first step if you need to, but here's what they're going to be with the leaves in increasing order. For the ones, we have 0, 1, 2, 3, 4, 5, 6 ones, 4 twos, 4 threes, 2 fours, 3 fives, 3 sixes, 2 eights, and a 9. So we can see how long this leaf is and where we might need to end up splitting the stems. So we'll have to look at the rest to see, but we can see this is already a pretty long one. So now we'll do the twos. And the threes. The fours, the fives, and finally the sixes. So we can see here that the ones is much longer than all the rest. So we go, oh, okay, this is probably where doing a split stem will help us. So that's what I'm going to show you in the next slide. All right, so here we're going to split each stem that we had into 2 stems. So we're going to have 2 zeros, 2 ones, 2 twos, 2 threes, 2 fours, 2 fives, and 2 sixes. So everything that's going to go on the first line for 0 is going to be numbers between 0.0 and that are less than 0.5. So the only number we have there was 0.3. So for the second line of zeros, it's going to be everything 0.5 up to 1. So we had a 0.5, a 0.5, 0.6, 0.6, 0.9, 0.9, 0.9, and 0.9. So now, again, we're going to split now each stem the same way. So for the first line of the stem, it's going to be 1.0 to 1.4, and the second line of the stem is going to be 1.5 to 1.9, since we only have 1 digit after the decimal place. So I'm going to continue to fill this in, and then I will talk some more at the end. All right, when we have everything filled in, this is what we should have. And you'll notice there's some, as in the case of the 5.0 to 5.4, there weren't any, so we have to leave that blank. But we can't just get rid of that line. We still need to leave it there to show that there were none in the 5.0 to 5.4 range. Same with the 6.0 to 6.4 range. So even though we didn't have any values, we can't just leave that part out. We need to put it there and just leave the leaves blank, because there were no leaves. Do not put a 0 there, do not put anything else there, just leave it blank. Another type of stem and leaf plot we use is called a back-to-back stem and leaf plot. So when 2 data sets have similar values, or have values that are similar enough so that the stems can be used, the same stems can be used, we can compare their shapes using a back-to-back stem and leaf plot. In a back-to-back stem and leaf plot, the stems go right down the middle, the leaves for one data set go off to the right, and the leaves for the other data set go off to the left. So it looks very similar to what we've done before with the stem and leaf plot, just this time we have a leaf on the left-hand side as well. Here's example 3. The following ages are winners of the Men's Wimbledon Tennis Championship and the Men's Golf Championship for the years 1968 through 2013. So the top table we see is the age of the Wimbledon winners, and the bottom table is the age of the Masters winners. So we're going to do some things. So the first thing we're going to do is we're going to construct a back-to-back stem and leaf plot for these data sets. And then we're going to see how do the ages of the Wimbledon champions differ from the ages of the Masters. We have 1, right? Those are the people in the 10s. Here are the people in the 20s, 30s, and 40s, and we have nobody older or younger than that. So we're going to do the Wimbledon winners on the right and the Masters winners on the left. So I'm going to write that down here. You don't need to do this, but I'm going to do it just so that way it is clear for you guys which ones are on which side. So we had nobody in the age of 10 to 14 win Wimbledon, but in the age of 15 to 19 we had 2 winners, a 17-year-old and an 18-year-old. In the 20 to 24 range, we had a 20-year-old, 6 21-year-olds, 9 22-year-olds, 3 23-year-olds, and 6 24-year-olds. And then now I will fill in the rest. So now we've done all the Wimbledon winners, and now we're going to do the Masters winners on the left. But you're going to notice this is slightly more different. So the smallest numbers are going to be closest to the stems, and as the leaves go to higher numbers, it's going to work outward. So for the 20s, we had 2 23-year-old winners of the Masters. We had a 25-year-old, 3 26-year-olds, 3 27-year-olds, 4 28-year-olds, and 2 29-year-olds. And then now I will fill in the rest with the same, where you see on the left-hand side that the smallest number is closest to the stem and works outward. Alright, so now we have all the Masters winners filled in on the left-hand side. So now we can answer question 2. How do the ages of the Wimbledon champions differ from the ages of the Masters champions? So if we look at the Wimbledon champions on the right-hand side, most of them seem to be in their 20s. A big bulk of the data is in the 2 range, right? Both of these 2s right here is where a big bulk of the data is. Versus if we look at the Masters winners, they seem to be in their mid-20s to early 30s is the bulk of the winners, even into their late 30s. So what we can say is Wimbledon champions are generally younger than Masters champions. So again, here's a practice for you now. The following are the runtime in minutes for 15 movies that were rated PG or PG-13 on the left-hand side, as you see. And then on the right-hand side, we have 15 movies that were rated R. So your goal here is going to be to do the following. You're going to construct a back-to-back stem and leaf plot for these data sets. And then you're going to interpret and see, do the run times of the R-rated movies differ greatly from the runtime of the PG or PG-13 movies, or are they roughly similar? So go ahead and pause the video right here, work through this example, and then resume the video. So the answers will be in 3, 2, 1. Here are the answers you should have gotten. So when we construct this, on the left-hand side, I have the PG or PG-13 movies. On the right-hand side, I have the R-rated movies. And there was only 14 R-rated movies. I know the slide says 15, but I just recounted. There's only 14. And there was 15 PG-13 movies. And now, if we look at them, okay, a lot of them run in the 80 to 90 minute range, even maybe into the 110 minute range. So if I were to look at them, there's roughly the same amount in that general range, and then a few that run longer. But there's not clearly a different bulk of the data. If I were to draw this, I can show you. Right, most of the data kind of is around here and around here. So next we have dot plots. A dot plot is a graph that can be used to give a rough impression of the shape of the data set. It is useful when the data set is not too large or when there are some repeated values. Example 4. So you're going to use table 2.18 below that presents the number of children of each of the presidents of the United States and their wives. So this is how many children each of the presidents of the United States had. Figure 2.17 is a dot plot of that for the table 2.18. For each of the values in the data set, a vertical column of dots is drawn with the number of dots in the column equal to the number of times the value appears in the data set. The dot plot gives a good indication of where the values are concentrated and where there are some gaps. So if we were to look back at the table, we see that there's 6 dots at 0. So that means there are 6 presidents that had 0 kids. There's 2 dots at 1, and we can see from there on. And we can even look at the very end of the line, there's 1 at 10 and 1 at 15. So we could look at this and go, well, it doesn't seem very common for a president to have more than 6 children, since only 4 presidents had more than 6 children. Time series plots. So a time series plot may be used when the data consists of values of a variable measured at different points in time. So suppose we have the following data. For the S&P 500, here are some values at different years. I want to construct a time series plot for this data, which we will show in the next slide. So if we look at 2005, the value was 1,248. So about right here. 2006, it was 1,418. It's about right here. 2007, 1,468. And I'm going to continue filling these in. And then now we connect them together. So this shows us our trend of what the S&P 500 did over these years. So a final note, in a time series plot, the horizontal axis represents time. So always use the horizontal axis or the x-axis for time, and the vertical axis as whatever we're going to measure. We plot the values of the variable at each of the time, and then we connect them with straight lines. So whenever you're doing a time series plot, you just need to remember those things. X-axis is time, y-axis is whatever we're measuring, and then once you plot all your points, just draw a straight line from the first point to the second point to the third point, and so on.